Hello, my name is Ritahan Mukhopadhyay, and this is the video portion of my final project for simulation. And what I'm doing is I'm going to simulate a pharmacy, specifically actually the pharmacy you see in the picture located in North Andover, Massachusetts, where I got my data from. So as you know, generally a pharmacy is a place where people go to seek their prescribed medicine, ask questions about their medicine, and they also have other services like vaccines. And generally, these places are accessible by either going in-store or in the drive-through, or just calling in. And mostly, if you're calling in, you're asking questions. You're not probably picking up medicine over the phone. And the actual goal for this study is to determine the average daily wait time for the drive-through, the in-store, and the phone queues. And I got this data from my friend who works at a pharmacy. So I just asked him several questions about the pharmacy that you actually saw before to get the data for the basis of this simulation. So just several of the assumptions. So we're going to assume our queues are FIFO and the pharmacy is at a fixed location. We're going to assume that our queues are unbounded. There's no balking except at the close. So if you're in line when the pharmacy closes, you'll be sent off. Although if you're the one getting served, you won't be sent off. Pharmacists help customers one at a time, and they do it independently. So if you're a customer, you'll only ever be working with one pharmacist. There's no restrictions on which pharmacist can help which customers. And there's also, at most, ever 3 pharmacists working at a time at our pharmacy. So the pharmacy's hours will be 8 a.m. to 8 p.m. Monday through Friday, 9 a.m. to 6 p.m. Saturday and Sunday. And we also have to take into account our distributions, which I chose based on the data my friend gave me. So for the inter-arrival times, I chose exponential distributions. And for the service times, I actually chose discrete distributions. So you can see here the setup for my inter-arrival time distributions, where I separated based on weekday versus weekend. And rush hour versus non-rush hours. Rush hours are 12 p.m. to 7 p.m. Monday through Friday. And it's not listed here, but the service times I have it set up either accounting for the probability of a customer just asking a question or picking up medicine, or an outlier case where it takes them a long time to get their medicine for whatever reason. So for that, I gave an 80% chance for a drive-through or an in-store arrival to take 4 minutes, 10% for it to take 1 minute, and 10% for it to take 20 minutes. For every phone call, I have a 90% chance of it taking 2 minutes and a 10% chance of it taking 20 minutes. And as again, all these assumptions were based on the data I got for my pharmacy. So the obvious entities and attributes, we have the pharmacy itself, which has its hours, as I've said. We have your pharmacists, who have their name and ID. In our simulation, we just refer to them as 1, 2, and 3. Their working hours. So the first pharmacist will work 8 a.m. to 8 p.m. Monday through Friday. The second pharmacist goes from 11 a.m. to 7 p.m. Monday through Friday, and then 9 a.m. to 6 p.m. Saturday, Sunday. And the third pharmacist goes from 12 p.m. to 8 p.m. Monday through Friday, and the whole 9 a.m. to 6 p.m. Saturday and Sunday. We also want to keep track if our pharmacists are busy, free, or not working. And finally, we have our customers, who have their type, which is either they're in the drive-through, or they're calling on the phone, or they're in store. And then the arrival time period is just equivalent to the pharmacy's hours. And now I'll just take you briefly through the event list. So we have the initialization, which starts the simulation at empty and idle conditions. All queues are empty, all the pharmacists are free. And then that will schedule your store arrival, drive-through arrival, and a phone arrival. And when in the store and drive-through and phone arrivals, those when the first arrival comes, we'll schedule a begin service. The begin service is parameterized by whether the store or the drive-through or the phone arrival is calling it, and also which pharmacist you're talking to. So the I parameter represents which pharmacist 1, 2, 3, and J represents whether it was a store, a drive-through, or a phone that reported to it. So these arrivals we'll call your begin service, and of course your begin service will subtract 1 from the respective queue, call your end service, and your end service will check if we can start another service if the queues are not all empty, or if the pharmacy hasn't closed based on the time clock. And the interesting thing here is that assuming that there are at least 2 queues that are non-empty, the end service will pick the front of the queue whose frontmost customer has the earliest arrival time relative to the beginning of the day. So whoever came first is who gets to get served. Additionally, this end service, if the time clock is past the end of the day, it will call close pharmacy, where it just closes the pharmacy. And close pharmacy will also call initialize new day, which basically starts the next day. And the initialize new day is actually the same instructions as initialize, except instead of setting day to 0, it just sets day to be day plus 1. And the check working hours, which is also called by end service every time, is to check if we need to add or take away pharmacists from the simulation if the time clock is within the correct range of the working hours. So now I'll just give you a brief overview of the code. And essentially, we keep track of our arrival times are in the drive-through, store, and on the phone, along with eventually the wait times and the service times. And we have our call to running the simulation, which, as you would expect, runs a simulation. And the run, where is it? The run simulation needs to generate customers first and has to generate pharmacists first, which is done down here. Oh, and we have our customer and pharmacist objects, as you can see. So your customer generator here generates your customers by the distribution, and your pharmacist generator also generates your pharmacists with their appropriate working hours and whatnot. So the simulation, just in while loop, runs, working through the list of customers that have arrived in the correct manner. And once the simulation run is done, it returns back to this main function that will do a bunch of analysis calculations. So like your covariance, your correlation, gets the average waiting time with the deviation. And then it also does the variance reduction technique, so using control variates and also conditioning. So as you can see, that is what the code is doing, the Python code. And get back. So for analyzing the output, we consider the fact that our study is of a transient process, which is due to the fact that the system gets cleaned out every day by the close pharmacy call, so we can't consider steady state measures. And so the most relevant transient measure for our study is the expected surgeon time, specifically the surgeon time for the customer queue. So for our results, we have a mean of about 11.9 minutes and a standard deviation of about 11.5 minutes for the drive-through, and that should say drive-through and in-store. I'll fix that. And 11.5 minutes and 11 minutes standard deviation for the phone. So we can construct our confidence interval, as you can see below. I've constructed a 90% and a 95% confidence interval based on this data I've collected. So we can also work on variation reduction using control variates, which is a method that uses your known variables with known expected values that have some correlation with our variable in question. And what I did is I tested the arrival times versus wait times, and also service times with wait times. And what I got is that we did get a reduction in variance. So with the drive-through and the in-store, which you should note do have all these same means and have all these same variances because they are in fact coming from the same distribution. I'm just generating the same like arrivals and services for each of them, because that is really what it is in the actual pharmacy. Anyway, so you can see we did get a reduction in the variance. Well, here I reported a standard deviation, but that's just the square root of the variance. And the same with the phone waiting times. And all the means, as expected, stayed approximately the same within about 3% of the original value. But the bigger reduction happened when I tried conditioning, which is a method of variance reduction that takes advantage of a theorem that proved that a conditioned estimator has a lower variance than its unconditioned counterpart. So I conditioned over whether the day was in the weekend or not, because as you noted, the weekend days had a different distribution for the arrival times. And to calculate the variance in this situation, I used a link provided in the slides to this paper from 1985. And my results, I got a massive reduction, a 96% reduction in variance for the drive-thru and the in-store, and a 95% reduction in variance for the phone queue, while staying within about 5% of the original average I got without conditioning. So those are the variance reduction methods I tried, and that's all I have for you. Thank you for watching my presentation.